We spent a lot of time in this stoichiometry talking so far about relating amounts of reactants with amounts of product, but now we want to spend a little bit of time talking about how we can relate amounts of reactants. So the ideas are the exact same that we've seen previously because it just comes from balanced chemical equations. So if we have a balanced chemical equation, for example, 2H2 plus O2 gives me 2H2O, we know that for every 2 moles of H2, you would react perfectly with 1 mole of O2. And so this ratio is what we call the stoichiometric ratio. It's determined by the number of the reaction coefficients for your different reactants. So if you want a perfect reaction, for every 2 moles of hydrogen molecules, you need exactly 1 mole of O2 molecules. And that would be the perfect relationship. You know, your ingredients would be mixed at the perfect ratio. But oftentimes we measure these amounts in grams. So how much oxygen is required to completely react with 4.5 grams H2. All right, so when we're taking a look at this, what do we want? When we see this, how much oxygen, that means right away that is a mass. Really any mass would do, because grams is given elsewhere in the problem. It'd be reasonable to think that it's going to be grams here again for your answer, but you do need mass. Unless you are asked explicitly for how many moles of this molecule or how many atoms or molecules, if it's not clear what it is, mass is always going to be what you want. How much necessarily implies mass, because how much implies it's uncountable, and everything else is a counting unit. So it's how many moles, how many molecules, how many of those. How much implies that it is mass, like how much money versus how many dollars. What do we have? Mass of H2. So we can see this kind of setup that we're looking at is still we want a mass. We have a mass of H2. That's a reactant. And what we want is the mass of a different reactant. But the thing is, they're still both related by this chemical equation, right? H2 and O2 have no relationship outside of reacting in this chemical equation. So I'm going to use the reaction coefficients, but they have to be in counting units. So the process for relating reactants in stoichiometry is going to be the exact same as the process that we saw previously for relating masses of reactants and products. Still that same 3-step process. Let's see it in action. How much oxygen is required to completely react with 4.5 grams of H2? All right, so if we look at this kind of setup, how much oxygen completely react with 4.5 grams of H2? And so when we see that word much, how much oxygen, that is going to be, when we see how much, that's going to be mass. So how many moles, how much always implies mass. The other thing, whenever, we can always kind of assume that we're looking for a mass measurement. That's an actually useful representation of amount. If you tell most people moles, it's not really useful in terms of how much it is. So we always want it to be in mass. So we're looking for mass. And when we see oxygen, we may be tempted just to say O atoms, but we do want to use O2 because that's really what oxygen is, kind of exists as. Elemental oxygen, if you remember, is a diatomic. So how much oxygen, our expected units would be grams of O2. Kilograms would also work with mass, but because we have a grams unit right there, it's likely that we're ending with grams here. And so we can see then that what we're doing is 4.5 grams of H2 to grams of O2. And so even though this is between two reactants, functionally, this is going to be the exact same type of stoichiometry we saw previously, because stoichiometry is based around reaction coefficients that come from balancing. Whether you're balancing two reactants or reactant and product or two products, it's always going to be the same rules. So whenever we're given mass like this, that's a pretty useless unit in terms of relating it to anything else. A good first step is to go from mass of H2 to moles of H2. And we want to get that molar mass. We do want to be careful It can be tempting just to look up the mass of H, but really H2 means it's 2 times H, which is 2 times 1.01 grams per mole. It's very common. This should be 2.02. It's very common mistake is to put a 1.01 there because you forget that you need to do, it's H2, so you need to multiply the number you look up on the periodic table by 2. All right, so we got that. Now we want to use our stoichiometry to relate H2 to O2. Again, we just use those reaction coefficients. So 2 moles of H2 for every 1 mole of O2. That just comes off of my balanced equation. And then finally, I want to go from 1 mole of O2 to 32.0 grams of O2. Again, we want to be careful for that molar mass. It's O2. Means that it's 2 times O, which is 2 times 16.00 grams per mole for the molar mass. If you mess up in both places, you get cancellation of error and you would get the right answer. But getting the right answer for the wrong reason is a perilous game. If you don't have that cancellation of error, you just get the wrong answer. So we want to use those 2's in both places. We're going to make some space to figure out that. We're going to say it is equal to 35.6 grams of O2. And so when we're relating reactants via stoichiometry, it works the exact same way as when we're relating reactants and products. Molar mass, reaction coefficients, molar mass. And those reaction coefficients only work in moles. So overall, we see the same idea. This pattern is going to come up again and again and again. So this mass-based representation that we get from stoichiometry is giving us the same information. It's telling us this perfect ratio. We know that previously it was for every 2 moles of H2, you would need 1 mole of O2. And what we can see here is that if you have 4.5 grams of hydrogen, the perfect amount of oxygen is 35.6 grams of oxygen, right? That is the perfect ratio that matches the 2 molecules of H2 for every 1 molecule of O2. And it comes from that stoichiometry calculation, which is why we call it a stoichiometric ratio. So if you have this mass of hydrogen and you want to know what the stoichiometric amount of oxygen is, it's 35.6. Okay, another video down. I think, yeah, that takes us over halfway through. Looking for any more questions on participation 615. See you in the next video.